Hello, everyone. Welcome to Molecular Universe MU-1 live demo. And I'm 𝐇𝐢𝐠𝐡𝐭𝐬, founder and CEO of SCS AI. And then with me today, we have 𝐇𝐢𝐠𝐡𝐭𝐬, Dan Hanna, Adam Matanas, Weijie Mai, and Yunya Zhang. And MU-1 is a big improvement compared to the previous version. And we're really excited to show you more. Before we start the demo of the MU-1 itself, I would like to share with you our motivation for why we started Molecular Universe. So the goal of Molecular Universe is really to replace R&D. And we all remember not that long ago, engineering drawing used to look like this. People hunting over big tables with big papers and then big rulers. And then all that got replaced with computer-assisted aided drawings, CAD, and also other softwares. Same thing in batteries. Battery R&D used to look like this, and actually in many cases still looks like this. And this is really inefficient. It's expensive, and it takes a long time, especially a lot of the battery development can take 6 years, 8 years, or even more. And also, for a lot of the next-gen battery startups, they can never outspend in R&D compared to the big companies. And the bigger companies can always spend more resource on scientists and also equipment. And this is why most of the next-gen battery development by these startups have been tried by the bigger companies. And this is also why we have seen a very limited success. So our goal is to replace this with Molecular Universe, and especially Molecular Universe in a box. And this helps level the playing field. So we're no longer competing on the size of the R&D resource and the size of R&D investment, but we can provide this Molecular Universe in a box that can democratize R&D. So to do that, to replace R&D, we need to follow the following flow. So first we start with a problem, and this could be an industry problem. Say we need to improve the low temperature cycle life of energy storage batteries, or we want to improve the fast charge of an EV battery or the high voltage of a cell phone battery. You start with a problem, and then we use this feature called Ask. And Ask is an agentic large language model where we can actually achieve senior scientist level. And then this recommends solutions. And the solutions are known solutions. And the way we do that is we reference a large database of public and private literature, and also our own domain expertise in the field. And then once we have this known solution recommended from Ask, we move to Search. So Search looks for novel solutions that have not been done before, but are based on the known solutions. And then we get inspirations for new molecules from Search, and then we take these to Formulate. And then Formulate is a feature where we make the battery materials and then test them in batteries. And then both of these are based on a large proprietary molecular maps, both molecule level as well as formulation level databases. And then we computed the properties of these molecules and formulations using both GPU accelerated quantum mechanics methods as well as machine learning accelerated property prediction. This is really key. And then we go to cell design. Design is basically where we can change anything about anything inside the cell, and then can get directional guidance if that's in the right direction. For example, Search and Formulate gives us thousands of recommendations. How do you know which one to focus on? And then how do you prioritize which one to start the experiment first? Design helps you helps give a directional guidance. For example, one would improve performance by 10%, another one would improve performance by 30%, and another one would actually hurt performance. And then you would filter out the ones that are not even in the right direction, and then only focus on the ones that are in the right direction. And then once you filter down to the candidates that are promising enough to actually perform the experiment, then we use predict. So predict is when once we actually build a cell, and then instead of waiting months or even years for several thousand cycles, we only need about 100 cycles as input, and then we can accurately predict the end of life. And then behind this is a large cell universe. So unlike other AI companies or other large battery companies, we actually systematically design and then collect battery data, cell level data that are designed for AI model trainings. So these are very different from the large scale manufacturing data in the public. These are purposely designed to train AI data. So this entire flow from starting with a problem, and then we ask, and then getting a known solution, and then we move to search, finding an unknown solution, a solution that's new, that's never been tested at the molecule level, at the formulation level, to design, to giving directional guidance if it's even in the right direction, and then to predict, to verifying the performance. This complete workflow is the new capability that we just introduced in MU-1, Molecular Universe 1. And in the previous versions, we only introduced ask and search, the first two features, and formulate, design, and predict. These three are the new features that we just added. So this complete workflow we're really excited about. And obviously, users can use these features independently, or they can use these features as part of a complete workflow. So I'm going to pass to Dan Hanna to explain the actual live demo.
Thanks, Qichao. So as you can see here, we have landed on the web page that hosts the online version of our materials discovery platform, which, as Qichao explained, is termed Molecular Universe. And to sort of reemphasize some of the points that Qichao has already made, Molecular Universe is really about accelerating the timeline for the discovery of new materials. We see that for a lot of cutting-edge battery technologies, the energy density, the performance under extreme conditions, and so on and so forth, improvements along these axes are still really driven by materials improvements intrinsic to what we decide to build the battery out of. And this platform is really designed to reduce that materials discovery timeline, both for batteries and also other chemical applications as well. So the landing page here is what we call the map. And I'll explain the map in greater detail in a few minutes. But overall, just to tie this back to the workflow that Qichao described in his slides, users are going to land on the map. And that map is really just a place where users can get oriented within what we call the molecular universe. And I'll sort of explain the technical details of this map in a second. But after this sort of introduction, the real starting point for a lot of research questions is going to be ask. So whether you're using molecular universe or not, research typically starts with a question. And ask is our way of providing the user with an interface for interacting with the molecular universe platform driven by natural language. You can literally ask the software a question. And we're going to go a lot deeper on ask in a few minutes, but just to show everybody, this is your way of asking the software a question and getting an answer. Once you have an answer, you might want to take that answer a little further. You might want to explore alternatives to the raw materials that are proposed by the ask feature, and that will often take you over to search. So search is really at a high level about finding other molecules that can replace or ideally exceed the performance of a query molecule. So if I have some raw ingredient, maybe my solvent, salt, an additive, and I'd like to find something to replace it with to improve the performance of my battery, Search allows us to go from one or more starting molecules, and we'll demo that in more detail later, to a list of molecules that should meet or sort of exceed the performance of the query molecules. Once we're happy with those raw ingredients, right now we're in the land of single molecules. Once we're happy with these molecules and we'd actually like to try putting them in a battery, one thing we can do to de-risk the transformation of those sort of raw ingredients all the way into a cell is to first look at how they're going to behave as a solution. So that's what Formulate is about. Formulate is where we're using physics-based simulation and machine learning to predict the properties of actual electrolytes. So now we've combined our salts, solvents, additives into a real formulation, and we are predicting the properties of that entire bulk solution. Once you're happy with that, once you say, hey, I think this solution is going to meet my needs, I can manufacture it, it has the properties I desire, you then might want to get a sense of how it's going to perform in an actual device, and that's where design comes in. So design now moves us from sort of the atomistic world where we're doing microscopic simulations and deriving bulk properties from that to the world of devices, where we can now assess how molecules added to an electrolyte will actually impact cell performance. And then finally, once you've decided that you actually want to take this formulation, put it in a cell, and take it into the lab, once you've got some testing data in hand, that testing data can seed our predict feature, which is really about accelerating the amount of time it takes to get to a conclusive answer in the lab. It uses early cycle life data to sort of predict the eventual fate of that battery in a way that saves significant time and resources when it comes to actually spending time testing those devices in the laboratory. So that kind of is just to connect what Qichao was explaining with how that workflow actually manifests in the software. And now maybe we can flip back to map, and I can briefly explain the technical details behind that map with a little more color. So
yeah,
what you
Dan?
Yeah, go ahead, Qichao. Yeah, please.
Yeah. So just to the audience, feel free to ask your question in the chat, and then we'll actually be answering questions as we go. And then I already see some questions are coming in, and then we can just go over the features. And then when we get to a feature that has relevant question, we'll just ask that.
Sure, sounds good. Okay.
Go ahead, yeah.
So when we get to the map, as I said, this is where a lot of users are going to land when they're first interacting with the software. And as I mentioned earlier, Molecular Universe is really about reducing the time it takes to discover new raw materials, new ingredients, out of which we can construct high performance next generation batteries. And those raw materials comprise what we call the molecular universe. So these are the molecules, the building blocks that our electrolytes and other parts of our battery are formed from. And this map is really just a way of explaining how molecules relate to each other structurally. What you're actually seeing here is a visualization of something called a molecular fingerprint. A molecular fingerprint is really a series of numbers that we use to describe a molecule in a way that is interpretable to a computer. And we take those molecular fingerprints and we construct them in a way that captures molecular structure. So that means if two molecular fingerprints are similar, the molecules that they were derived from are structurally similar. They have similar functional groups, they have similar connectivities, and so on and so forth. The trick with molecular fingerprints is they're extremely high dimensional because they need to contain a lot of information. So they're not 2D, 3D, 4D. They're 512 dimensional. And that is something that we can't really visualize. And so what we do is we borrow techniques from a subfield of machine learning that is known as dimensionality reduction. And we apply those dimensionality reduction algorithms to yield a two-dimensional map that captures those notions of similarity and those relationships from the high dimensional space. So that means that when two dots on this map are close to each other, those molecules have similar structures. And when two dots are far away, those molecules will tend to have very different structures. And generally people may spend some time on the map, but in addition to being a landing page, what we'll see a little bit later is that this map is a great way of understanding how diverse a given body of search results is. So we'll talk a little bit more about that when we go deep on the search feature, but you could keep it in your mind that this map is a way of telling you, the scientist, the user, this is how much of the molecular universe you've explored. with a given body of results. And maybe for some applications, you want to stay in one region of the molecular universe. Maybe you know where you want to be. I want molecules that are similar to this one. But maybe in other cases, you've hit a wall, or you're looking for a completely novel breakthrough. You may want to explore those less explored regions of the space. So with that, like I said, we'll talk a little bit more about how this map integrates with search once we get there. But now I want to move to the next stage of the workflow, and I'm going to turn it over to Adam to talk a little bit more about our Ask feature.
Yeah.
Dan, sorry. So one question came in. The map, does it include only lithium relevant molecules, or flow batteries, or other chemistries?
So in sort of the most technical sense, our database is agnostic to the working ion. So this database, particularly the one that's highlighted here, this is solvents, additives, diluents. These are actually largely neutral organic molecules, which in principle could apply to lithium, lithium ion, sodium, and so forth. However, I think we'll see that later on, the sort of first use case that we've really focused on excellence in is the lithium ion use case. We have, as you'll see a little bit when we go deeper on Formulate, we have some other common working ions right around the corner. So far, a lot of these molecules are really focused on that rechargeable battery use case that is maybe a little different from the flow battery use case, but that's certainly something that we anticipate the software expanding to encompass in future releases.
Adam, you want to cover
Yeah, I'll describe the Ask feature. So Ask is basically a natural language interface for interacting with the molecular universe software. It's sort of been around since the first version of the software at MU-0. But we've made a large number of sort of behind-the-scenes improvements to it that I'd like to go into here between the original release of MU-0 and this release of MU-1. So the first thing you'll immediately notice is that we actually give you now multiple different options for how you want to interact with our software. So you have an option for basically 3 different sort of compute speeds for the Ask feature. So Lightning will reply within about a minute and give you sort of if you're interested in a very quick response, potentially for some simpler questions. Pro gives you a sort of very high quality, sort of well-researched result. Often will take about 5 minutes or so. And then Deep Space, I'm going to go more into Deep Space in a few minutes. But Deep Space is actually an extremely powerful system that uses actually a whole team of LLMs, a multi-agent system, to actually produce an extremely high-quality response, a research-grade response to your question. And so I basically want to start off by talking about sort of what has been sort of the core strength of Ask sort of since the beginning, which is our sort of proprietary literature database. So we've actually, so basically behind the scenes, Ask will use a procedure called retrieval augmented generation, or RAG, to basically look up information in the literature to provide an answer to your question. So, so one of the things that people really like to use Ask for is just sort of producing sort of essentially sort of reviewing a lot of sort of relevant literature. As you can see here, it looked at 78 different papers and patents, reviewing the relevant literature and sort of providing that sort of literature review capability to the user. And sort of one thing we really want to focus on is providing sort of a very broad, but also very high quality set of content for Ask to use. And since MU-0, we've actually quadrupled the number of different documents that are available to it when answering user questions. We've added thousands of additional papers from literature. We've added hundreds of different sort of internal documents and internal expertise from our own expert scientists. We've also added tens of thousands of patents. So you can see here, Ask can retrieve literature, and it can retrieve patents related to your question here. And it can use this basically to, so obviously you can use this just sort of as a, provide me sort of a literature summary of this field. But also it is sort of one of the things that Ask does really well. So when you ask some sort of battery related question, it actually goes and looks at these references. So unlike other types of large language models, which might be more likely to sort of hallucinate or potentially use sort of lower quality news sources just from sort of searching the internet, Ask will actually sort of use these very high quality sources, and it will sort of cite them in the answer. It will always provide sort of the links for you to go and directly check the sort of ground truth source. So that's something that we think is really important for large language model assisted workflows, is being able to quickly sort of check like where's the large language model getting its sources from, making sure that those sources are reliable. In addition to sort of increasing the size of this database, we've also made a number of behind the scenes improvements to ensuring that the papers that get retrieved are sort of more relevant to your query. So one of the biggest changes is we've actually trained our own battery specific embedding model, which basically, so the embedding model is basically a piece of software that sort of converts questions into sort of abstract mathematical representations that are then used to sort of determine which papers are more relevant to them. We basically trained our own model on battery data in order to ensure that the sort of papers that are getting found are actually sort of relevant to the question within a battery context. So we'll basically be sort of returning more relevant results than a traditional system that hasn't been fine-tuned in this way.
Yeah.
Yes?
Adam, there's a question. Does the software have any way of distinguishing between papers on the same subject, but one is of higher quality and the other is junk?
Well, our way of distinguishing that is basically by not including junk in our paper database in the first place. The Ask model is also, it does like sort of understand what the citations are. So it will sort of potentially be more likely to return results from high quality from like the highest quality journals. But we endeavor to basically make sure that only high quality results are included in the database and in the first place. So we avoid a situation where like it's going to cite some like random news article that like may not have been particularly well thoroughly vetted. We endeavor to include sort of only sort of high quality peer reviewed work here.
Okay.
Yeah. So one other thing that we've done is we've actually, in addition to sort of enhancing the sort of ability of Ask to sort of retrieve relevant literature and patents, we've also tightly integrated it in with the rest of the Molecular Universe software. So now you can see that Ask is actually capable of going and querying the Molecular Universe database on its own to retrieve data relative to the user query. So obviously you can use this just for sort of creating these sort of nice visualizations here where you can sort of very easily create tables or otherwise look up data. So sort of in a very nice sort of natural language interface. But also, as I'm about to show you in a bit, it can actually use this as part of more complicated queries where it can look up molecular properties from our database and use that information when deciding how it best wants to answer your query. One other thing I'll quickly highlight is that you can also, we also sort of improve the visualization here. So Ask, whenever it finds a molecule that was in our database, you can sort of very quickly go and hover over it to see sort of all of the relevant molecular properties. So now I want to sort of move into Deep Space, which is sort of our most powerful and exciting feature in Ask. So Deep Space is sort of a feature that's designed to provide a sort of very detailed, very well-researched answer to your question. So here we're basically going to enter this entire battery system into the model. And we basically, we're asking the system to recommend additional additives that can improve the cycle life. And so Deep Space, because it's such a sort of a powerful system, it will actually ask you some sort of clarifying questions first. So to make sure it sort of best understands exactly what you're looking for. So for instance, are you looking for like industrial compounds? Are you looking for academic compounds? You know, how novel are you willing for your compounds to be? Do you want your compounds to be from the literature, or do you want like sort of new, potentially novel molecules? So I'll ask you sort of all of these questions about exactly what you want, so it can produce a like highly tailored response to your precise use case. So you can go ahead and answer the questions, and then what it can actually do is it can actually produce sort of entire new battery formulations on its own, using sort of, and it can actually go look in the Molecular Universe database for entirely novel molecules that have never been studied before and provide those to you. So you can see here, it's recommending these 4 different additive packages. And you'll notice that in this last additive package here, you see this MU-1 molecule. This molecule is not a molecule that's ever been studied before. This is an entirely new molecule that was recommended by the algorithm as something that you could potentially put in a sort of small concentration into your system, similarly with these other types of molecules. So it can sort of, based on how you answer the questions, it can sort of range from, you know, for instance, this type of this type of additive package, where these are sort of molecules that are sort of well known. It can sort of tune the concentrations based on what it has learned from literature, and then it can go all the way to recommending potentially entirely new, very sort of experimental additive packages. And so, yeah, you can see sort of the full list of like, these are all the compounds that are sort of known to work. These are all the compounds that are sort of found in the molecular universe database. And so we sort of think this is potentially a really powerful tool to sort of jumpstarting sort of battery research, regardless of whether you're sort of looking for, I have a system, I want things that I know work, like what are the sort of best, literature proven additives, or if you're like in an earlier stage of development, if you want to find like entirely novel molecules that could be useful, it can do sort of basically all of that. And we're really excited to see what you guys can build with this tool. So with that, I'll move on to search and hand it back to Dan.
Yeah, great. Thanks, Adam. So as Adam mentioned, there's kind of a number of different ways to engage here. So ask is a way of asking the platform a natural language question, and search is instead not driven by natural language, but driven by a molecule instead. So you have a molecule in mind, and you'd either like to look up its properties directly, or maybe you'd like to leverage the sort of massive underlying database along with the sophisticated search machinery we've built to find a molecule that might perform better than that molecule for some application. And to unpack that in a little bit more detail, one way to sort of frame this is that ask is a way of getting answers sort of given a context. And that context can come from you because you've specified it in the question that you're asking the platform. That context can also come from the literature. You want to see, how have other scientists, how have other companies solved this problem? How would human knowledge sort of guide me to an answer? But other times, you might want a perspective that is driven more by structural similarity and property comparisons. In other words, I think that this molecule is going to be more reductively stable than this molecule, and so on and so forth. And I think this speaks a little bit to one of the questions that I see here from an audience member about whether or not this is self-limiting. In other words, if there's decades of work that has been done on lithium-ion chemistries, and we're sensitive to those decades of work, we incorporate them into ask via the literature database that we've given it access to. But then the question is, how do we break out of that? How do we find new discoveries and unlock sort of brand new battery chemistries? And that's where search can come in. With search, you can take anything ask has given you, or alternatively, you could skip ask altogether, and maybe you have a sense of where you would like to start. You can plug a molecule into the search box, and by the way, the search box has a number of input modalities. So here we've searched with an abbreviation EC, which is ethylene carbonate, a very common battery solvent, or a solvent for battery electrolytes. But you can directly input a smile string, which is a textual representation of a molecular structure, or you can actually sketch a molecular structure here on the sketch pad that is provided. So one of the things that's going to happen when you click search after you input a molecule is you're going to have, no matter what, if that molecule is in the database, that molecule will be presented to you. And so if you were to just type in EC and click search, you would just see EC as a result. That's just a way of doing a property lookup. But as we're demonstrating here, the platform can go quite a bit farther than that. So some of the things that we've done here are we've checked this box that says find friends. Find friends means give me other molecules that I could replace this one with. And in many cases, we're hoping for molecules that would actually perform even better, but sometimes it could be issues of availability, it could be issues of novelty, but we want a different molecule that should perform similarly or better to the query molecule. You'll notice that to the right of friends, there's a box. Right now that box says solvent because ethylene carbonate, or EC, is a solvent. You can actually choose the type of ingredient you're looking for. So that might be a additive, that might be a salt. We'll actually talk about salts on a separate tab because it's a different class of raw material. But on that Find Friends menu, you can choose the category of ingredient you're expecting your query molecule to fill. So EC is a solvent, so we chose solvent here. Intelligent Find Friends is something that you can enable to spin up essentially additional search machinery in the background that's powered by heavier machine learning models and large language models, and will evaluate your search both with an eye towards additional context that you provide and also with a more detailed evaluation of each of those potential search results that influences how we rank them when we present them to you. So if we scroll down a little bit further, what we can see here is that there's this box that allows us to specify natural language constraints on the search. So here we've typed display only molecules of fluorine. That's a way of essentially guiding the search. I, the expert user, I happen to know that I'm only interested in molecules that are fluorinated for whatever reason. So I'm bringing in my domain knowledge and I'm inserting it into the search here via that box. There's also additional levers we can turn here that we'll take actually maybe we take a peek at the search results first just to show that this these molecules. Okay, we're still searching. Okay, so I'll unpack the rest of this. I didn't see that the search was still running. So that's that advanced ML machinery that I talked about, chewing through this in the background. What these other boxes do, so in addition to that natural language context where we can say, okay, only show me molecules of fluorine, we might also want to control the balance of structure and properties. So right now, you'll see this slider up at just above the context box where we typed in that natural language request. This is our search range. And what this is effectively doing is controlling the balance of how important structure is and how important properties are. If you slid this all the way to the right, that's what we call nearby friends. So you might recall that this map is a way of grouping structurally similar molecules together. What nearby friends means is only show me results that are in a particular region of this structural space. I want things that are very structurally similar. And we find in practice that a lot of times when developing batteries, the expert users who are actually taking advantage of the software will have a pretty well-defined idea of what sort of molecular backbone or template they want to work with. And there can be a lot of reasons for that, ranging from manufacturing, synthetic accessibility, safety, commercial availability, what have you. But oftentimes we find users might actually want things that are sort of gentle structural variations on a known backbone. And in that case, you're kind of wanting to push that slider to the right. On the other hand, maybe you found that an entire class of molecules isn't really meeting your needs. Maybe it's something about your battery chemistry or your cell design is incompatible with carbonates or incompatible with this template. In that case, you actually might want distant friends. These are going to be things that have similar physicochemical properties, so similar redox potentials, similar melting point, boiling point, flash point, similar solubilities, and those, but they're going to look structurally very different. And so this gives you kind of control over how much you want structural similarity to matter sort of or not. And then below these different boxes for cathode, anode, salt, primary solvent, and desired performance metric, these basically give the search engine a little bit more info about what it is you're hoping to do. And it will try to tailor those results to your purpose. So maybe you're looking at an LFP cell with a graphite anode and you specify a salt and a solvent and you're looking to improve low temperature cycling performance. The model in the back end that's in controlling the search will incorporate that context, and then those searched molecules will be sensitive to those parameters that you specified. So now I think the search maybe has finished.
Yeah, I think there was an issue with
yeah.
Try
again.
Okay.
Why don't you explain how we define friends again? Lots of questions about that, and then we can move on to the salt and then the solid-state maps. Just quickly cover that.
Sure. So in this case, that's a great question. So in this case, a friend is a molecule that should perform in the same way as your query molecule, but ideally be even better. So that means if I'm searching for EC as a solvent, a friend of EC is something that I could use as a solvent in my electrolyte instead of EC.
What's the definition of friends, the properties? Can we list them all? The 20 plus properties and then structure?
That's right. So under the hood, what that algorithm is doing in the most basic sense is first it's computing a structural similarity score. So I mentioned that we have these molecular fingerprints for everything in the database. We're looking at how similar all of these molecules are to our query molecule. And we're building up a measurement of how similar each of these structures is. We're then also looking at how similar are the properties. So here, because we're working at the raw material level, our proxy for performance is the properties of those raw materials. And that could include things like the highest and lowest energy, the highest occupied molecular orbital, the lowest unoccupied molecular orbital, which are sort of related to the redox stability of that molecule across the battery's operational range. And we're also looking at the electrostatic properties of those molecules, which will ultimately determine at how they kind of operate in solution, how they dissolve other molecules once we incorporate them into the solution phase, and then a few other properties. And we're also building up similarity measurements for those properties. So now, regardless of the other options you've specified, we're always going to take into account to some degree, what are those structural similarity scores? How similar are the molecular structures? And how similar are the molecular properties? Mm-hmm. And then depending on the value of that slider, right, you could go for nearby friends or distant friends, the relative weight of those two things is going to be controlled by that, in addition to some of the parameters that users can enter. So for example, the things that are very, very important for an NCM cathode may differ slightly from the things that are important from an LFP cathode. And the way that we weight the properties, the reductive and oxidative stability and so forth, is going to be sensitive to the values that users input for those fields. You can also leave those blank to effectively get an agnostic perspective. Like pretend you're just developing an electrolyte. You may not even know what cell you're going to put it in yet. The results are perfectly valid without any of those fields filled in.
Mm-hmm. And then also talk about how we computed these properties, what techniques we used.
Yeah, that's right. So the database itself, so at the raw material level, the properties are, for the most part, labeled by quantum chemistry methods. So we have an enormous kind of effort to label all these molecules using density functional theory in-house, and some of these properties are derived from the density functional theory calculations. However, there are other properties that are not directly accessible to quantum chemistry methods at the single molecule level. For example, the melting point, boiling point, and flash point of the pure solutions, or the pure forms of those compounds. And so what we've done in that case is we've actually trained machine learning models to make those predictions. And so what you're seeing when you actually look at the properties for each of the molecules that you're getting as a search result is you're seeing a mix of things that are derived from quantum chemistry methods, as well as machine learning models, which are trained in many cases actually directly on experimental data.
Yeah. And then also let's just quickly cover the salt and then the solid state maps.
Yeah. So maybe we can click over to salt. And so the salt, you'll see that this sort of looks at a surface level, looks very similar to the solvents, additives, and diluents database. The only difference here, the key difference, is that the solvents, additives, and diluents, as I mentioned, is predominantly neutral organic molecules. Those neutral organic molecules are things that tend to be compatible with battery electrolyte formulations, but we're really covering the neutral molecule space. An equally important part of electrolyte design is the counter ion. So there's always a counter ion. So you'll hear about LiPF6, LiFSI, so on and so forth. Those anions that are providing a balance to your working ion, like lithium, also have a tremendous impact on how your electrolyte is going to perform. And so this salt anions tab is really about getting recommendations for new salts, being able to search for friends of salts, being able to look up the properties of those anions that are going to coordinate lithium or whatever working ion. And so this overall has a very similar functionality. We are able to search for abbreviations, like for example, TFSI is something you can put directly in there. You can enter a SMILE string, you can draw a molecule, and so on and so forth. We also have the Find Friends functionality work enabled and shipped for our salt anions, and it works in much the same way as the neutral organic molecules do, where a friend is something that we expect should have similar or better performance, but ultimately offers a substitute for the molecule in question. And in practice, I think what we find is that friends are a great way of sort of doing a guided walk through the molecular universe. You know, you're an electrolyte scientist, and you want to
Yeah.
see
Yeah,
what can I try? What can I try next? Yeah, go ahead.
In the interest of time, let's just quickly cover solid electrolytes and then formulate and then design and then predict. We do have a lot of questions coming in about the different tiers and data security. So we can cover that.
Okay. So solids, you'll see solids look a little bit different here. So solids are a way, here we can search for solid electrolytes. So again, this is still sort of electrolyte focused, but here this allows you to search for solid materials out of which you would create a solid electrolyte for a solid state battery. And so here, what these ultimately give you is a list of properties. In this case, these are predominantly experimental properties that we've compiled, which are relevant to the operation of solid state batteries. And so maybe in the interest of time, we can kind of address specific questions about this later. Maybe in the interest of time, we can jump ahead to Formulate.
Yes.
So, okay, you've worked with Ask, you've worked with Search. Now you have a set of raw materials in mind, but you're not ready to take it to the lab yet because you don't know if you can actually make this electrolyte. You don't know if it's going to meet your needs. You want to know, is it going to dissolve my salt? Is it going to conduct ions? Is it going to be in a viscosity and melting point and boiling point range that are amenable to me actually getting it into a battery cell effectively? And all of those things are still within reach for us to predict on a computer. And that's what Formulate is really about. So Formulate allows a user to specify those raw ingredients and actually trigger what's called a molecular dynamics simulation, which is a way of simulating how atoms actually interact with each other in a way that is similar to how they would interact in a beaker in your lab. So what Formulate is really about is getting the properties of your electrolyte as it exists in a bulk material. And if we scroll down a little bit, I won't go through each of these specifically, but we have a set of properties here. These are the things that at SES we have found are sort of the most relevant for assessing the effectiveness of an electrolyte, and we can compute those things. The amount of time these simulations take can vary depending on the properties that are requested. It ranges from just a couple of days to more than a week in the case of some of these properties that sort of require very good sampling to produce accurate predictions of. I will note, just as briefly, that we have some benchmarks shown lower on the page. One of the things that I think sets us apart here is that we've made a considerable investment in an extremely high performance force field that gives us state-of-the-art predictions for pretty much all of these properties. And if we scroll down a little bit, I think we don't need to unpack the plots, but there are some plots that show how well we agree with experiment. And so this I'll sort of set aside. I just wanted to make people aware of this if they want to read more about the technical performance of this machinery. One thing I would like to show very quickly, if we go back up and click New Analysis, this is how users can actually trigger one of these simulations. So today, as I mentioned, this is something that we are continually expanding, but today lithium is available as a working ion. We have some common anions available as a anion with which to make a lithium salt. And we can choose up to 2 of these, and we can specify their fractions. And then moving down further, we can also choose up to 3 solvents. So it's very common in practice to have multiple solvents present and multiple salts present. And so we do support that to a certain degree. And once we've added all of our solvents and all of our salts, there is some basic sanity checking. You won't be allowed to submit a simulation if, for example, the fractions of your ingredients don't add up to 1. So we do some basic sanity checking. But assuming everything's good, you'll be able to submit the configuration, and then you'll receive an alert when your results are available. And I believe we have some pre-computed results we can take a look at very quickly. Yeah, so if we pop that up, you'll see these kind of reported values for all of those properties that we compute. And at the very bottom, we also provide a plot of the radial distribution function and the coordination numbers. And this is really about understanding how the atoms in that liquid tend to position themselves relative to other atoms. So what are the average distances between the species that are present in my solution, and how are they kind of clumping together in the simulation? And this gives people a lot of info that helps kind of further lets them apply their intuition about how these things are going to perform. So with that, This allows you to say, hey, I'm happy with my formulation. I actually think that I would like to try making a battery out of this. And at that point, you've kind of moved from the raw materials world, where you've gone from molecules to liquids by going from ask to search to formulate. You're at the liquid stage now. To carry things into the world of sort of the cell level, that's where design comes in. And that's where I'm going to turn it over to my colleague Yunya to explain a little further.
Okay, just keep sharing. Looks like it's
I can keep sharing. I can.
okay. So while we get it back up, a lot of questions in the comments about commercial engagement and who's been using Molecular Universe. So almost every battery company is using Molecular Universe, and we're really excited about this. This goes from materials companies, electrolytes, cathodes, to cell companies, to auto OEMs. Almost every battery company is using MU. And then we actually made, our users have made several interesting discoveries off of MU, Molecular Universe, including a new additive for low content silicon, about 12%, a new additive for medium to high content silicon, and then a new additive for high voltage LCL. And also we are developing a few more. So, and the way the battery companies can use this include three. One is subscription. They can subscribe to Molecular Universe, and we offer both cloud and also a hybrid of cloud and on-premise. So the 5 features, ask and search, these are primarily relying on our data, and there's a large language model behind. So these most users would use this on the cloud. But formulate, design, and then predict, as we'll see later, these rely on customer input data. So these 3 we can actually put in a box and then install on-premise. So it's a combination of cloud and also on-premise. And then for now, we are very focused on batteries, because we found that these AI vertical companies, you really need to have high quality data and domain expertise. Otherwise, there are lots of AI companies that do similar work, but without this high quality data, the performance is not as good. So for now, we're focused on batteries, electrolytes, and then expand to cathodes and other materials. But there has been other companies in industrial chemicals, in agriculture, pesticides, that have approached us and that have asked us to build Molecular Universe for those applications. And then down the road, we might consider that. But for now, we are absolutely focused on battery use. So. Yeah, want to explain the design?
Sure, no problem. So today I'm going to introduce the design function in the MU platform. So the goal of the design is to provide a semi-quantitative reference about how the new electrolyte additive impact the cell performance. So behind the design actually is an AI model that is trained by SES internal cell testing data, which is very well controlled and has a very consistent benchmark to ensure the model efficiency. So in the current version of the design, we can select the cell chemistry in this box. Now we select the NCM811 as the cathode and the 12% silicon plus graphite as the anode plus the carbonate electrolyte. After we selecting the cell chemistry, the cell specifications will appear in this window. And this actually is the benchmark cell we tested. So in the model prediction actually is based on the comparison between this benchmark cell and a cell with identical cell specification plus 1 new electrolyte additive. So in the next window, we can put any molecule smile, whether this molecule is inside the MU database or not. So Don, please copy the the first one, yeah, this one, yeah. So right now the amount of the additive is fixed at 1.9% weight percent, but in the future we can change this number. So this is an additive that was recently reported by a Chinese company. It has a very interesting structure that has two DTDs plus one EC at the center. So it's kind of a mixture hybrid structure. So based on our model prediction, this structure can give you positive impact on the cycling performance and Coulombic efficiency, but slightly damage the rate performance, probably due to the thicker SEI and CEI, leading to a slightly higher internal impedance. If you want to have more explanation, you can go down and click the LM analysis. This actually is the function connected to our ask function, but it will take some time. So let's load another results. So yeah. So on the left side, you can see.
Go ahead. It's okay. Yeah. Today the performance is a bit slow. I think some issues with the AWS just globally.
Yeah. So on the left side, you can see the records, the molecules you searched before. Here we load another one, which is a closed friend of FEC. So you can see this molecule actually has a positive impact on both room temperature and 45 degrees C cycling performance, and has a slightly damage on the rate performance. The LM actually provide some reasonings and references as for your reference. So in the future, the design function will be much expanded. Firstly, that we will cover much more chemistries, not just the NCM 811 plus silicon. Near future, we will expand to these 4 common chemistries, and in the future, we can cover more. Secondly, is that
yes,
not
so,
just go ahead.
Yeah, I do think this is important. So a lot of people ask, how is this tool different from other tools out there? So one of them is these data. So a lot of the AI companies don't have domain data, and they naively think that by collaborating with the battery company, they can just get their data. But that's very naive, because most battery companies don't have such AI model training suitable data either. Most of the big battery companies, the type of data they have are not suitable for AI model training. So this kind of data, we've been a battery company, and then we continue to have these battery cell assembly capabilities. And then we intentionally build a diverse range of chemistries, and then a diverse range of materials inside, testing conditions. And then we even intentionally reduce the yield, so we have a good balance of positive and negative signals. No other battery company would do this, but we do this so that this model is trained on the highest quality and most diverse set of data. This is a really important thing. Domain expertise and high quality data is what's really important for AI verticals. And then this is what sets apart Molecular Universe from other similar models.
Yes. Actually, this is the uniqueness of SES AI. As Qichao mentioned, is that secondly, we will cover not just the additive, but also like solvents, salts, or even electrodes in the future. And finally, we will cover much more testing conditions, including like a high temperature storage or fast charge. So if you find some suitable molecules inside of the design, and you decide to put it into the real cell, then we can go for predict function to further improve the R&D efficiency. So Weijie can introduce the predict.
Yeah, so this design feature allows users to virtually evaluate how a new additive impacts the cell performance without the need to physically synthesize the molecule or build a prototype cell. This makes it a very powerful tool for early stage material selection. However, even if a promising molecule is identified using design, it still needs to be synthesized and tested in real cell to validate the performance. And for example, if the cell is you are expecting the cell to reach 3,000 cycles, it will take over 250 days to just verify that cycle life. So this will significantly slow down the time to market cycle. And that's exactly why we created this feature, Predict. So Predict allows users to upload early cycle data from a battery cell, and our AI model, which is trained on a vast, large data set covering diverse cell chemistries and designs, will estimate the long-term performance of that cell. On this page, you can see an example. So for this battery, we actually cycle the cell to reach 80% capacity, which takes about 1,261 cycles. So our models can make life prediction using only the first 100 cycles of data. And the predicted cycle life is 1,321 cycles, which is within 5% error of the true value. Now, if you compare this with a simple linear extrapolation using the same first 100 cycles, you see that if we use linear extrapolation, it will only predict the cycle life to be only 800 cycles, which is significantly underestimate the actual performance. So in this case, our predict function reduces the time needed for performance verification by over 90%. Without compromising accuracy. This means faster innovation, lower cost, and smarter decision making. And using Predict is simple. Maybe Dan can hit on new prediction. Yeah, so the user is only needs to upload a CSV file with basic cycling time series data, such as current, voltage, and time. From the first 100 cycle. You're welcome to upload more, but we need at least 100 cycles. And then the model is trained to be chemistry and design agnostic. So it means that there's no need to enter cell chemistry or design information. The cycling data of the first 100 cycle, that's all we need. But that being said, if you are working with specific cells, we can fine-tune the model using your cycling data to further improve the prediction accuracy. And then once the data is submitted, data processing and model inference will take just a few minutes. Maybe then you can go back to the record and show the result. Yeah, if you view details, so you can scroll down a little bit and see the results. So for this cell, the user has uploaded 200 cycles, and the cycle life is predicted to be 2,806 cycles, which significantly reduces the time needed to test the cell. So in summary, Predict is a tool to accelerate the validation process of new electrolytes or new cell designs by providing accurate prediction of cycle life using early cycle data. Yeah, I think with this design and predict function, we close the entire R&D loop by providing tools to validating performance without building the cell, and then after building the cell, you can still use Predict to accelerate the validation process. Yeah.
Yeah, Adam, can you quickly show the tiers table, the different tiers, base and enterprise? A lot of questions on that. I think
sure.
Go down. So the new MU-1, because from the previous versions, we had lots of interest. So we actually added more tiers. We have the individual tiers, which go from basic to research, explore, and the teams. Click on enterprise. Enterprise, we're adding 3 layers within enterprise, 1, 2, 3, and joint development. And this is where almost every battery company is in at least one of these tiers. And then, for example, we start with subscription, and then the car company or the battery company starts using enterprise 1, and then they move up to enterprise 3, and then we identify a material, and then we can actually have the material contract manufactured, and then we supply the materials. Recently, we announced a JV with the electrolyte manufacturer. So we can actually supply the materials that's discovered by us or the users using this platform. And then for each one, we list out the details around data security for cloud or on-premise, and people can read this yourself. So overall, I hope the users get a sense of the workflow from ask to search to formulate to design and then predict. And then really MU-1 compared to the previous versions is a much more complete workflow. And then it's starting to accelerate R&D and then even replacing part of R&D. And then we have lots of questions, but in the interest of time, we cannot cover all the questions. We'll try to take down the names and then get back to with your answers after this. But really appreciate all your attention, and then feel free to try this MU-1 for yourself. Go to molecular-universe.com, and then we have these different tiers. So yeah, and then if you have any comments or suggestions, always welcome. So thank you all.